In this example, let's consider a 64-pound mass that elongates a spring by 4 feet. We stretch it an additional 15 inches and let it go, causing the position of the mass to oscillate up and down with a damping coefficient of gamma equals 8 pound-seconds per foot. Let u of t be the position in feet of the mass t seconds after it is released. We want to set up the initial value problem, modeling the position of the mass, and solve it for the function u of t. The differential equation modeling u will be given by m times u double prime plus gamma times u prime plus k times u equals 0, from what we learned in the last video. We're given the damping coefficient gamma equals 8, but we will need to find the mass and the spring constant k on our own. To find the mass m, we will use that the weight, 64, is equal to mass times gravity, where gravity is given by 32 feet per second squared, and thus the mass is 64 over 32 equal to 2. The elongation length L, which is 4, along with the equation weight equals k times L, gives that the spring constant k is 64 over 4, which is 16. So now that we have all three constants, we can put together the differential equation. 2u double prime plus 8u prime plus 16u equals 0. Now, this application also includes initial conditions. Since the mass was extended an additional 15 inches, which is 1.25 feet, we have that u of 0 is 1.25. And since the mass is released without any initial velocity, we have that the initial velocity is u prime of 0 equals 0. Together, this gives us the initial value problem, 2u double prime plus 8u prime plus 16u equals 0, with u of 0 equals 1.25 and u prime of 0 equals 0. To solve this, we'll start by getting the general solution by looking at the characteristic equation 2r squared plus 8r plus 16 equals 0. Since this can't be factored, we can use the quadratic formula to find the roots. The roots r1 and 2 will be negative 8 plus or minus the square root of 8 squared minus 4 times 2 times 16 all over 2 times 2. The denominator simplifies to 4, while the discriminant, 8 squared minus 4 times 2 times 16, simplifies to negative 64. So we get that the roots are negative 8 plus or minus 8i all over 4, which reduces still to negative 2 plus or minus 2i. Now, using the root r equals negative 2 plus 2i, we have the general solution, u equals c1 e to the negative 2t times cosine of 2t plus c2 e to the negative 2t times sine 2t. And now that we have the general solution, we need to impose our initial conditions to find c1 and c2. Using that u of 0 is 1.25, while on the other hand, it's c1 times e to the negative 2 times 0 times cosine of 2 times 0 plus c2 e to the negative 2 times 0 times sine of 2 times 0, where cosine of 2 times 0 is just 1, and sine of 2 times 0 is the sine of 0 is 0, and our exponentials e to the negative 2 times 0 are also 1. So the right-hand side simplifies to just c1, leaving us with c1 equals 1.25. To use our other initial condition, u prime of 0 equals 0, we need to compute the derivative using the product rule. Computing u prime, we get negative 2c1 times e to the negative 2t times cosine 2t minus 2c1 e to the negative 2t times sine 2t by taking the derivative of the first term minus 2c2 e to the negative 2t sine 2t plus 2c2 e to the negative 2t cosine 2t by taking the derivative using the product rule of the second term. Now, evaluating u prime at 0, we get that 0 equals u prime at 0, which is negative 2 times c1 plus 2 times c2. Again, using the simplifications of sine of 0 equals 0, cosine of 0 equals 1, and e to the 0 equals 1. Now, since we know that c1 is 1.25, we can rewrite the right-hand side as negative 2 times 1.25, or negative 2.5, plus 2c2. And now adding 2.5 to both sides and dividing by 2 gives us that c2 is also 1.25. So we can conclude that the position of the mass is given by u equals 1.25 e to the negative 2t times cosine 2t plus 1.25 e to the negative 2t times sine 2t. Although we've found the solution u, we can analyze it further. Notice that we can factor out e to the negative 2t to get u equals e to the negative 2t times 1.25 cosine 2t plus 1.25 sine 2t. And rewriting the right-hand side as a single periodic function, using that r equals the square root of 1.25 squared plus 1.25 squared, which reduces to the square root of 25 over 8, and that delta equals the arctan of 1, which is pi over 4, we get that u equals e to the negative 2t times the square root of 25 over 8, which is r, times cosine of 2t minus pi over 4. In this form, we can see that the solution is nearly periodic, but with a decreasing amplitude due to the factor e to the negative 2t. That is, the mass will oscillate periodically due to the cosine function, but with a decreasing elongation from its equilibrium position due to the e to the negative 2t factor. As t increases, e to the negative 2t decreases. In the physical interpretation, this decreased elongation is due to the damping in the system. So the mass will oscillate up and down on the spring, though each oscillation will move less from its equilibrium position than the oscillation before. This is what we would expect to see for a mass on a spring slowing down.